So hello, actually, yeah. Today we'll talk about flaky test management, and I'm kind of intro about me. I'm kind of newbie, working in the field for 2.5 years already, and yeah, please go easy on me. I'm still a kiddo, so I'm from Kazakhstan, Central Asia. So let's start. So from the scratch, what the flaky tests are. So, like when you flip a coin, you're not sure about the outcome, whether it's a tail or a head. Same happens with a flaky test. You're not sure about the outcome. Like, it's not stable, basically. So you can see from the graph, test login. So it passes, then fails, but within the same software version. Software version means that the code hasn't changed, the data hasn't changed, the feature flags were not turned on, the feature switches. But still, for some reason, the test was producing this type of outcome. And on the other hand, let's define what the stable test means. So if the test is constantly failing, it doesn't mean that it's flaky. It means that we identify the bug or something is not working correctly. It's not that the test is flaky. But if the test, so that's what we stable tests are meant. And if the test is passing consequently, that means also stable test. So here is like the differences between those definitions of terms. And the next one. So example of when you can encounter those flaky tests. So let's say we have a developer and he would like to raise a pull request and then merge his changes. But in the middle, we have CI/CD checks. And when the tests are failing inside the CI/CD checks, developer would assume, let's rerun the CI/CD checks because the tests are not really revealing any issue. And he does it, and we see on the second attempt the tests all are passing. And actually, the developer is allowed to merge his changes into the main branch, right? But on the other hand, the developer is kinda losing the trust to our tests first. The second of all, we are also diminishing again credibility, and then we are wasting our resources by rerunning the test second time, the CI/CD checks. So yeah, so here as you can see, we zoomed in, we run the test failed, merge blocked. Developer thinks, let's rerun it, and passes. So this is when you can encounter flaky tests, basically. Next one. And not only us are facing with those issues. Big tech companies such as Google says that 16% of their 4.2 million tests are also flaky in 2017. Then there is data of Microsoft. They say 4.6% of the tests from five analyzed projects were flaky. And Firefox says that 100 up to 150 new flaky tests are identified weekly. Next one. So this is kind of a research of how is the flaky test in the industry, but let's talk about the solution of it. So this is theoretical solution. When we talk about the management part, I kind of assume that we need to prevent from flaky tests of intruding into our repository. We need to detect flaky tests if they're already inside the main branch, and we need to for sure disable them, right? So this is what comes to my mind when we talk about management. So let's start with the prevention. So the prevention strategy solution will be a reliability gate. So let's zoom in the figure. So here you can see we have a main branch, then raising a pull request. We compare our pull request, like a feature branch, with the main branch. If you identify new test, we run that test multiple times. And if all tests pass successfully, or like a 90% depends on your threshold, then we can continue to the next CI checks. But if at least one test failed, then we block the merge, basically. So this is kind of simple solution to prevent from flaky tests. And with the detection part, this contains a bit of a mathematics, so let's go. So we will talk about some models of how to detect flaky tests. The first one is unweighted model with versions. Next one is a weighted model with versions. Like unweighted and weighted is quite similar, just weighted has a recent run matters more in weighted model, like last week data has more value compared with the last 30 days data. So this is what weighted model. But today we will talk about unweighted model, because if we will go further with decay factor, it will become even challenging to explain this type of stuff. So let's go on. And another one that we are implementing in our company is without versions, because we just don't have data for with version solution. So weighted model without versions also. So just a difference, showing it on the figure. With versions looks like this. Test sign up, every first version had 6 runs, and yeah, etc. Test sign up had consequent runs, right? And what those versions are actually. A new version is created every time software code, test code, or dataset, such as like feature flags, if you do that in your company. If they are adjusted, the new version was created, then we just create, basically we create a new batch, basically like this. So a new version, unweighted model with versions, an example could be like a release branch. You have like a mobile application that you release once in a 2 week, or like once in a week. And for example, 26.11 was one release, another one is 12, and etc. So for that reason, I suggest using unweighted model with versions. So why using versions? Because code is frozen, and the mirrors production software, many runs per version, so utilize that one. And the next one, we are using that currently in our company, is using on master branch, because main branch kinda is very dynamic, it changes, but still we are running our end-to-end test against the production, but the production is changing in a rapid pace, so that's why we are using that without versions. So now let's go deeper into that unweighted model with versions details. So in order to compute flakiness, we need to have a data, right? So for that reason, we care about dataset. Then mathematical models that we're gonna apply that will help us to detect flaky tests. Mathematical models that we're gonna talk today would be flip rate and entropy. We'll go further in that. It's not that hard, actually. The formula is very simple. And then there is a confidence score, accompanied with the score we are providing as a flakiness. A confidence score is needed because we need to ensure that data we are computing our flakiness is enough, number of runs are enough. So, and then confidence score will be also computed with the help of margin of error. We will also talk about that. That was a bit challenging one, but we'll still cover that. So the dataset, we are actually fetching data from multiple sources. Those are scheduled runs on master branch. Then we are taking from CI/CD runs, such as like manual execution. Developers are going to Jenkins and manually selecting which test they would like to run. And test execution records are stored in like a JSON format. You can see from here there is a title, status of a test, duration, and started at and completed at times. So here is the data. Next one is a mathematical model, which is a flip rate. Flip rate measures the test instability. So what we basically care about is that we want to see the transition of test status. So you can see from the image figure 5 that test transitioned from pass to fail, fail to pass to fail, and fail to pass, right? And it kind of flipped 4 times out of possible 4 times. So we just divide number of flips, actual number of flips, divide by number of possible flips. And when we ended up with some kind of value. So in this case, it will be 1. And the result of the score is from 0 to 1. And the 1 means the test is absolutely flaky. And from the image of illustration, you can see it is flaky. So that's how it looks. Then there is entropy. Entropy is just a formula. Basically, we add probability of passing multiplied by logarithm of probability of passing plus probability of failing multiplied by logarithm probability of failing, and add them together and put the minus sign before. So yeah, it's just a formula and nothing fancy. So example on how to apply those both models. Let's see the illustration. Here we have 6 runs. Number of possible flips are 5. And number of flips actual, you can see from the image, is 2, right? So for flip rate, that would be 2 divided by 5. This is 0.4. And actually, we can also rank the test flakiness, like whether it's slightly flaky, how's it called? Slightly flaky, flaky and very flaky, basically. Yeah, with the help of that number 0.4. So in that threshold classification, that would lie in very flaky classification, basically, for the flip rate range. Entropy of probability of test passing is 5 out of 6. You can see it from the image. And probability of test failing is 1 out of 6. And we just put it into the formula that I've mentioned earlier. So that would end up with a result of 0.65. And the classification threshold from that table, we can, from that table would be very flaky classified, basically. And you might be wondering about in the long run. So we kind of took a very small snippet of test runs, right? But what if we take for the last 30 days inside the versions? So in order to have some value at the end, we just take the average. And how we do that, so the first one we already computed, entropy and flip rate. For the second one, the test was stable. For the third one, it was also stable. And we ended up with a value of 0.22 for the entropy and 0.13 for the flip rate. And as I said, we need to accompany it with a confidence score because the user who sees the flakiness score should understand on how many numbers of runs that value was based. So for example, for this case, we have the formula such as 1 minus 1 over square root of n. N is a number of runs. So basically, if you put it into the formula, you will end up with a value 0.73 and multiply that by 100. We ended up with a value 73% confident. 73 depends on your threshold. If you have a lot of data, you can even go up to 90, but in order to have 90% confidence, you need to have 101 number of runs, basically, which is, I don't know if it's possible, but it is possible if you have a lot of data. And the second approach, so if you want to have 95% of confidence with very small data, so for example, 95% confidence for flip rate 0.13. For that, we will use margin of error. The formula looks like this. T static will be default for 1.76 multiplied by standard deviation, which we'll compute in the further steps. Then number of flip rate scores, which is, you can see it from here. Yeah, standard deviation is 0.17. Don't want to go deeper into that resulting flip rate scores because from my previous presentation I understood that it's pretty hard to explain or to even understand, I guess. But whatever. So the margin of error we end up is 0.08. And what does that mean? Is that we're 95% confident that flip rate score is 0.04 to 0.22. Basically, the true flip rate score lies somewhere there. But as you can see, the range is very big, not narrow. So for that reason, we understand that data is not enough. And if you have similar case as our company, where we don't have enough data, and we cannot employ that employ that employ that methodology. So we chose the without versions approach, where we collect raw results over the last 30 days, basically test execution records, then include only tests with at least 10 execution records if we want to compute flakiness, and then apply those mathematical metrics which I showed you before. And step 4 would be just compute general confidence score. And that's all, kinda. And how would we measure the performance of our model? So this would be implemented with the help of a metric called precision, where true positive divided by true positive plus false positive. And if you're wondering what true positive and false positive means, so true positive is where both the actual value and predicted value are matching. So we kind of found out the flaky test, basically. And false positive is when we made a mistake, basically. We found out a stable test and predicted as a flaky. And disabling strategy is also not that hard, very simple. So running all tests, but filtering out flaky ones after the execution. You can see it in the step 2, where we filter out the flaky test and only based a pipeline pass or fail status based on the stable test that we defined previously. So yeah, if the non-flaky tests are passed, pipeline could go further, and if non-flaky tests were failed, then pipeline fails, and yeah, just check the report, I guess. And it wasn't based from my own mind. I'm not that I don't like the word smart, but it's a research paper which I took. It's a ranking flaky tests at Apple. So yeah, we basically referenced our implementation and this slide presentation based on their work. So you can find it over here. Key achievements of their, I have still 12 minutes. Okay, key achievements of their results is that flip rate performed better than entropy. Why we need 2 formulas is that flip rate is dominating compared with entropy. Entropy is just for fall over, just for accompanying the flip rate, basically. Yeah, and Apple stated that their repository become 44% more stable compared to how it used to be after applying their solutions. And if you have any suggestions, advices, also questions, feel free to reach out on LinkedIn. Yeah, so here's the QR code. So I think that's the end of the slide. Yeah.
All right. Once again, I failed. How was it? Challenging, stressful?
I don't know if it was useful.
How is the audience? Welcoming? Warm?
I'm not sure.
we will judge based on the questions.
Sure.
All right. We have a few questions. First of all, I'm quoting: "Flaky test is a myth. It is an outcome of bad scripting. Don't see the point of counting flaky tests instead of fixing them. What's the point in your case?"
Yeah, that's true. That's why we have the prevention strategy. But if it's already inside the repository and no one is going to monitor all the a lot of tests that we have inside the main branch, basically. And yeah, we just want to make our decisions based on the data that we have in hand. If it's a small company, I guess there is no need to implement the flaky test management. But if there is a lot of contributors into same repository, in that case, there is a need for that. But prevention strategy is more than enough, actually. Detection is just in case if the company is pretty big.
Okay. You ended the presentation with summarizing the outcomes in Apple, like how they improved their stability. Do you see similar results in Vinted, in your company, where you apply this?
Not yet, because we are only started like 4 months ago to apply this solution. So we gathered already data. Now we are fetching feedback from developers on whether the tests that we assigned as flaky, are they really flaky? And we will define our solution based on the precision that we receive.
Okay, and that leads to the next question. So what problem does knowing if flaky test is more flaky or less flaky? What problem does it solve?
Priority for developers to fix it as soon as possible or not. So.
All right. Did the idea to count all these things come from management or QA, and what was expected from these calculations? What do you do with all these flaky test data?
So idea was on volunteer base, because I was writing my bachelor thesis 8 months ago, and I asked my senior Zded, can they help with the topic? And we ended up with this topic basically. Next, what was the question other than that? Why we need the I forgot the question.
What you do with all this data?
So what we want to have is a stable checks. That's all. We want to just have stable pipeline.
And that's reasonable wish to have that.
Yeah.
Yeah.
Yeah. I guess.
All right, and probably looking at this audience, how many of you have actually applied your bachelor work in your actual work? By the raise of hands. Like less than 10 hands, I see. And this is a good example of applying actual science in actual practice. So thank you for sharing your story. Thank you for sharing all those fancy formulas. And thank you for accepting this challenge to come to us.